And the last talk in today's session is talk by Professor Gregory Berkolaiko. The title is Morse Theory for Eigenvalues of Self-Adjoint Families. Please, Grisha, you can start.
Thank you very much. Thank you for the introduction and getting my title right. I forgot what I submitted, so I improvised on the slide here. This is a joint work with Igor Zelenko, who is a professor at our university, specializing in differential geometry. And the paper was just accepted to Invenciones, and the referees really worked hard with us to help us organize our results. So really, I should credit the anonymous referees as well, just in case they're in the audience. So let me first set up the problem slowly. What are we looking at? So the idea is we have an operator that depends on parameters, and we choose an eigenvalue somehow ordered. Maybe we look below the essential spectrum, then for semi-bounded operator, then the ordering is obvious. And we'll look at the eigenvalue, and we want to understand the minima and maxima and critical points of this eigenvalue as a function of many parameters. So this is for operators, but we can apply risk projection. So we will restrict our attention to matrices. So first of all, sim n will denote the space of n by n real symmetric or Hermitian matrices. So depending on the field, the results are a little bit different. So we'll I'll show results in both cases. And assume we could order the eigenvalues and that they're continuous functions of the underlying parameter. The ordering, I will assume, goes from the lowest one up, as is traditional in mathematical physics. So these eigenvalues are real valued because our matrices are self-adjoint. We also have a manifold, which is smooth and compact for some results, but really our results are very local. So I'll basically take manifold mostly as R to power D, but for some results you need compactness. So smooth compact manifold of dimension D. So M is my parameter space, and I have a family F which maps this parameter space to the self-adjoint matrices. So again, this is my parameters, and this is parametric family of operators. What's the task of this talk? What do we want? We want Morse theory for the case-ordered eigenvalue of this family. And I will give an introduction to very quick introduction to Morse theory to explain what I mean by this. But in words, Morse theory gives a connection between the number and the type of critical points of a function, and on one side of the connection, and on the other side of the connection is the topological invariance of the underlying parameter manifold. So that's what I want to connect. All right, so this is the main question for the talk, but let me explain why are we interested in it from mathematical physics point of view. So this is a simple example. It's known as generalized SSH model. SSH model was a model for ethylene molecules, generalized it at some not so nearest neighbor interactions. For all practical purposes, it's an infinite periodic graph. So it's H acting on L to Z to L to Z. The Z labels are here, 0, 1, 2, 3, 4, 5, etc. And the operator, if we write it in the matrix form, in the natural matrix form, it gives weights for the connections. These connections have all weight V. These connections have all weight U, and the vertical connections have all weight W. So it's one periodic. Therefore, to analyze it, it's natural to apply Flecke-Bloch. Basically, we replace the infinite operator with a parametric one parameter family of 2 by 2 matrices in this case. Why 2 by 2? Because the unit cell that gets repeated periodically is of size 2. So this guy gets repeated by shifts left and right. So the spectrum of the whole thing H will be the union of the spectra of this HK, which are 2 by 2 matrices, over physicists call it Brillouin zone. For us, it's a torus, one-dimensional torus, minus pi to pi circle. I won't go over through details how this matrix is formed. Basically, you look at the connections and think what gets shifted where, and multiply it by complex phases. But the matrix HK that appears here is this matrix. And if we plot the eigenvalues of this matrix as functions of K, there are two eigenvalues, of course, it's 2 by 2 matrix, and these are the eigenvalue curve, lambda 1 and lambda 2. And you see lambda 1, for example, has 2 maxima and 2 minima. This and this are the same, but the minima are different levels. The spectrum, according to this formula, the spectrum of H is just the projection of the values of the upper curve and projection of the values of the lower curve. So there are two intervals of the continuous spectrum. But this function also gives us the density of eigenvalues. And here is the plot for the density. So on the upper part, what we see is the following. I took numerically very, very long parts of the graph. I cut it off. It's a finite matrix. I computed the eigenvalues and I plotted the histogram. Okay. There is a curious feature here. There are exactly two eigenvalues here at 0, and that is the exciting part of SSH model having to do with topological insulators. But in the limit of longer systems, this is insignificant. So let's ignore it. Now, below this sort of numerical density, I have the same curves because this one is now lambda axis. I want it to be permanent lambda. Okay, and you can see that the density of the eigenvalues is the density of values of these functions. This function is called the dispersion relation. That's why in the title I use the words dispersion relation. In particular, you see these peaks here, which in the limit will correspond to singularities in the eigenvalue density. These peaks arise from this local minima and maxima that we see here. So minima and maxima of dispersion relation translate into singularities of the eigenvalue density, and these singularities are called Van Hove singularities. Olaf says he cannot see the bottom part of the slides. Does anybody else have this technical problem? Olaf says he cannot see the bottom. I can see it on my other computer, so I think Zoom is okay. I think it's Olaf. I think it's your settings on the screen. Yeah. All right.
Let's see. We see these red and blue curves with lambda 2 and lambda 1.
Yeah, and like this point is in the bottom now, and I think you should be able to see it. How would I actually make it stick? This bit. All right, Olaf figured it out. Good. Q. All right, so these guys are called Van Hove singularities. They were observed before Van Hove, but I suspect, I don't know for sure. I just read the paper of Van Hove, and it's from 1940s. And he was visiting Institute of Advanced Sciences. At that point, he was a physicist. And he really used Morse theory to prove that these singularities are to be expected. And I think at that time, Morse was just down the corridor from Van Hove's office. So my point in this example is that this critical points of the eigenvalue curves and surfaces, they do matter. They come up in physics. They are important. Another example that many of us have seen, Olaf for sure, is tight binding graphene, tight binding model for graphene. We have this hexagonal lattice. It's not really graphene because I'm allowing myself different potentials at blue and red vertices. So I allow in principle this, in graphene, they're all the same, they're all carbon. But mathematically, I can do whatever I like. And now it's two-dimensional periodic lattice. So I do the same Flequier-Bloch transform. I get this 2x2 matrix because everything is just this bit repeated periodically. It's here, it's here, it's here, and it's here. So it's 2x2 matrix, but depends now on two parameters because we have two periodic system on K1 and K2. And here is the plot of the eigenvalues of this 2x2 matrix as a function of these two parameters. This points, as now almost everybody knows, they're called Dirac points, so conical singularities, and they explain some spectacular physical properties of graphene. If we perturb, so this is A equal to B, if we disturb this equality and have A different from B, this conical singularities resolve and they become one maximum and one minimum. The point of this example is to remind ourselves that the eigenvalue surfaces are in general not smooth. So they have singularities, and singularities are quite typical. But what we would like to do is to say, even though this one is not a smooth point, it's still a maximum. It is still a maximum, but we cannot use calculus to describe it because we cannot do second derivative tests. Second derivative just doesn't exist. and this one is minimum, and again, we cannot use second derivative test. And if we have more parameters, like in 2-dimension, it's clear that this is the only picture that can happen at the isolated singularity. But in 3 and more dimensions, there could be more exotic pictures, and visualizing it like I did here is very problematic when you have more than 2 parameters. So we would like to get some still first derivative test, second derivative test to tell whether a point is a minimum and maximum, or what it is. That's the idea. Some of you know that I'm very fond of counting zeros on graphs, on eigenfunctions on graphs, and doing some kind of distribution of the number of zeros. So this is nodal statistics, and there also one of the tools is introduce a magnetic field, and then the number of parameters is the number of cycles in the graph, so it's unlimited. And then you start looking at the surfaces and trying to figure out what happens at this points where 2 surfaces touch. Another one of my motivations is the question of minimal spectral partitions, pioneered by Terracini, and then Helfer and Hoffman-Austinhoff, together with Terracini, proved some spectacular results there. In that case, the manifold of parameters M is super complicated. Here, it's still a torus. It's high dimensional, but it's a torus. Here, it's probably not a manifold. It's maybe, if we're lucky, it's stratified space. So this is a kind of shining goal of application, but we're not there yet. Quite natural application actually comes from quantum chemistry. There is a method of studying kind of configurations of molecules using so-called potential energy surfaces. So a molecule is described by spatial configuration, something like this. That's maybe water or something like this. So the parameters here is the angle and length 1 and length 2. Depending on these 3 parameters, we have a potential energy, Hamiltonian, coming from these 3 atoms, and we can describe electron in this potential energy. But as parameters change, the eigenvalues, discrete eigenvalues of the electron also change, and the idea is that kind of as electron is. The electron wants to be at the minimum of energy, and therefore it forces the molecule to assume certain configuration which corresponds to the minimal energy of the electron. So they are studying these potential energy surfaces, and they cannot do very complicated molecules because the number of degrees of freedom goes up very fast. But this sort of conical singularities play an important role. They can do conical. They're just starting to do triple singularities. So we are building mathematical theory for their purpose. So that's my motivation, fairly long motivation for the question I asked. Let me maybe recall what is Morse theory on some 2-dimensional examples. So currently, I'm assuming my M is a surface, so it's 2-dimensional, and that I'm given a function which is twice differentiable. So this is the classical Morse theory. There are 3 types of critical points that are non-degenerate. I'll explain what is non-degenerate. They are minimum, like this, saddle point looks like this, and maximum looks like this. We associate to these critical points so-called Morse index, 0 in this case, 1 in this case, and 2 in that case. What are critical points? Critical points are like points on M where the gradient of F vanishes. And then we can do the second derivative test. So we can compute the matrix of second derivatives of S, the Hessian. And this is a symmetric matrix. We will look at the number of its negative eigenvalues, assuming there are no zero eigenvalues. Look at number of its negative eigenvalues, and that's mu here. So Morse index tells us in how many directions the point will roll down the slope. So here there are two directions, and here there is only one direction where the legs go on the saddle point. So this is the main kind of the spectacular result, I'd say, of Morse theory. Let's see mu denote the number of critical points of index mu. And let beta mu be mu's Betti number, which is the rank of the homology group, integer homology group of the manifold. So for all practical purposes, what I do, I go to algebraic topology book and I look it up for the manifold I'm interested in. So these are known, and the theorem says that there exist non-negative numbers, non-negative integers, so that the number of minima are at least Betti 0 plus an extra bit, and the number of index 1 points are at least Betti 1 plus some extra bit plus the previous extra bit. So these are equal, and these are equal, and those will be equal until the very end. And this fact that the same R appears in two places, it allows us to give an estimate on the number of critical points of, say, index 3 if we know something about index 2. In other words, this shows that you cannot just have an isolated minimum appearing by deforming the function. If you deform the function and create another minimum, it will create another index 1 point as well. This bunch of equalities we can write, okay, they're called inequalities because this is the inequality part, that they're all non-negative. We can write these equalities in terms of generating functions. So we take generating function of these guys, generating function of these guys, and of those guys, basically. So generating function of the Betti numbers, that's called Poincare polynomial over integers. Generating function of the critical points is called Morse polynomial. So basically we add together over all critical points, we add t to power the index of the critical point. And the previous equalities that I showed can be now written very compactly, that the difference between these guys is divisible by 1 plus t. This divisible by 1 plus t shows that the critical points can only be created in pairs, times some remainder term which has coefficients non-negative. So this is the inequality that's headlined in the theorem. So let's do a very simple example, classical example from like page 3 of Milner's book on Morse theory. My manifold is 2 torus, and my function, I visualize my function as the height of the points on the torus. So this is my torus, and the height is f. So this is the maximum of the height as a function defined on the torus, and this is the minimum. And these 2 points are saddle points, because in one direction height goes up, and in the other direction along the inner circle it goes down. And here vice versa. On the inner circle it goes up, and on the surface of the donut it goes down. So these are critical points of index 1. So what I have is I have 1 minimum, 1 maximum, and 2 critical points of index 1. They coincide with the Betti numbers that we look up. So all these r's are basically 0, and in this case, we can say that the Morse, so for all of this, the Poincaré polynomial of the torus is 1 plus t squared. That's the information we look up. The Morse polynomial of my function f minus pm in this case is 0, so it is indeed divisible by 1 plus t because it's 0. Here is a deformed torus. So topologically, it's still torus. It's still a function defined on the torus, but we deform it. Basically, means the height function got modified. I deformed it, creating 2 maxima now, but at what cost? At the cost of creating this point, which is an additional saddle point. So now we have 3 saddle points, 2 maxima and 1 minimum, and I messed it up. So this guys should be here. And then PF, the Poincaré, the Morse polynomial is 1 minimum, so 1 plus 3 saddle points, 3t, plus 2 maxima, 2t squared. And PF minus PM is now t plus t squared. It is divisible by 1 plus t, and the remainder is a polynomial. The ratio is the polynomial with non-negative coefficients. So on this example, more classical Morse theory works. So now we want to not just extend it to non-smooth functions. That has been done. Specifically, we want to extend it to non-smooth functions, which are eigenvalues of some typical matrix families. The fact that the eigenvalues of self-adjoint matrix families is some restriction on the type of functions we can get, and hopefully we can get some interesting results out of it and some sort of derivative tests, because the underlying object, let me go to my initial slide again. I didn't write it, but it's very important. So this guy is smooth. So my matrix family has smooth dependence on the parameters, but the eigenvalues are no longer smooth. But maybe we can somehow differentiate the family and get some first, second derivative tests. That's the hope. So I have 25 minutes to show you whether the hope is realized or not. So this is summary of what I have been saying verbally. So the difficulty is the lack of smoothness of individual eigenvalues around points of multiplicity of the corresponding eigenvalue. And here are a couple of examples. This is a mock example of this Dirac point in graphene. Take this matrix with 2 parameters, x1 and x2. I'm ignoring the fact that I promised the compact manifold because we're really looking locally around 0.00. And the eigenvalues we can compute, and the right cone. This is eigenvalues, surface of eigenvalue lambda 1 and lambda 2. And if we look, for example, at the level curves of the lower one, then they're nice circles. And the main idea of Morse theory is that critical points are points where the level surfaces, level curves experience a topological change. What's the topological change here? It was circles, 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 and then nothing. That's a topological change. More precisely, you need to talk about sublevel sets, but never mind. We'll stick with just curves. The second family is like this. Not much difference. Instead of minus x1, I have 2x1 here. Here are the eigenvalue surfaces. And the point of this example is to show that this point of multiplicity 2 is no longer a critical point. In the topological sense, it is not a critical point. The level curves go like this. Yes, they develop a non-smooth point of non-smoothness, but topologically, these all things are the same. And if you can imagine maybe perturbing this matrix, say with plus I minus I epsilon, something like this, perturbing this matrix family, you can imagine these things will get separated and they'll get smoothened, and there is no critical point. Here, you smoothen it, you get a maximum. Here, you smoothen it, you get nothing. Can we distinguish these two situations by not looking at pictures of eigenvalues, but by looking at the family F? How to look at this and predict what's going to be. So main result number 1, we are ready for it. It's very simple actually, but just a bit of notation. So sim nu was the self-adjoint matrices of size nu. With plus plus, they're positive definite matrices. I'm using it a bit loosely because sometimes my matrices are negative definite. It's up to the sign. So let's start with a point on M where kth eigenvalue, we choose a label K and we focus our attention on kth eigenvalue of our matrix family. Belongs to symmetric matrices n by n, but lambda K experiences an eigenvalue of multiplicity nu strictly less than n. Then we want to formulate a condition on the critical point. So critical point in the classical sense is we would do lambda K dot, right? If we have just one parameter, we would do lambda K dot. If we have just one, sorry, maybe not one parameter. If we have multiplicity nu equal to 1, we can compute lambda K dot. And there is Hellman-Feynman formula or eigenvalue perturbation formula or Kata-Frelich formula that says that this lambda K dot is equal to the eigenfunction, normalized case eigenfunction, applied to my matrix, differentiated psi k. That's the classical case for nu equal to 1. So what object are we looking at for higher nu? It's kind of the same object. So we have here U, the matrix of normalized eigenvectors. There are nu of them. So these guys are now eigenvectors. Well, eigenvectors here and eigenvectors transposed there. Or you can say that U is an isometry from R nu to the eigenspace of eigenvalue lambda K. And we differentiate, this is F dot, we differentiate our family F with respect to the parameters in some direction V, and we sandwich it with our eigenvectors. So this, like physicists know as degenerate eigenvalue perturbation, basically. So the result of this is a nu by nu matrix that depends on the direction in which we're looking to differentiate. So we consider it as a map from the direction on the manifold, from the tangent space on the manifold where we want to differentiate, into nu by nu symmetric matrices. And here is the first theorem, first derivative test. As classical first derivative test, it has a hole in the middle. Like it's there are some cases that are undecidable. So you will see it here. So what are regular points? Regular points is such points where we compute this operator V to this expression, and we'll look at its range. And if we find a matrix B that is positive definite in this range, then it's a regular point. And the idea is really very simple. The idea is that in this direction, then like here is my point of multiplicity 3. And this is my direction V in which I am getting a positive definite matrix. If the matrix is positive definite, that means eigenvalue curves look like this, coming out of this point in this direction. So it's not a critical point. They're all going up with non-zero derivative. So that's the statement may look a little bit complicated, but the idea is very simple. Although proof is non-trivial because it's a topologically regular point, so we need to show that there is a deformation of the sublevel sets. For the critical point, it's almost converse. So we look at the orthogonal complement of the range. This orthogonal complement is computed, of course, in the symmetric matrices. And if it is one-dimensional and it's spanned by a positive definite matrix, so if my range contains a positive definite matrix, it's a regular point. If it's orthogonal to a positive definite matrix, it's a critical point. Of course, in between, there is a semi-definite matrices, but we know that first derivative test, like on x cube, tells you it's a critical point, but maybe not critical. It's the degenerate critical point. So there are these nasty boundary cases there as well. Okay, so this is the first, the simple theorem. And maybe it's a good time to stop to see if there are any questions before I launch into, I'm not sure what I will launch into. Depends how many questions there are. I guess no questions, then I will launch into the next stage. And the next stage, I was planning to work this example out by hand, but I think I have only 15 minutes left, so I'll spare you the details. The details are really unsophisticated. It just shows that all that is needed here is a bit of linear algebra, and then you get some interesting information. Anyway, I'll show you pictures. This is my family. It's a very simple case. 3x3 matrices 2x2 matrices depending on 3 parameters. Because there are now 3 parameters, it's hard to visualize eigenvalues. Like even if I compute this numerically, how do I visualize it? I have trouble. Maybe heat map, 3-dimensional heat map, not sure. So we can sort of do sections. We can set z to be 0 and look at xy plane. How the eigenvalues of this guy depend on x and y when z is 0. So this is the picture. So z equal to 0. And there is a parameter c right here. And depending on parameter c, I have these 2 possible pictures. The interesting feature here is that the 2 eigenvalue surfaces, they intersect along a circle. It's, I don't know, sometimes it's called Mexican hat, the upper surface, because there is kind of flat bit and then curves around. But it's a tilted Mexican hat on a head. This is head and this is Mexican hat. So the eigenvalue degeneracy happens on a circle, and maybe these guys are critical points, like at the ends. Maybe not. It's not so easy to tell. We can look at the level curves. They look beautiful, but again, this is hard to read. If we look at instead, so this is xz. So if we set y equal to 0 and look at xz plane, this is a better picture. Turns out to be a better view to look, but I'm cheating here. I know where to look. I did my first derivative. So I'm showing you the good pictures. If we don't do first derivative, we don't know where to look. But here you can see a couple of points that really look like maxima and minima, depending on which sheet you are on. And this don't look like maxima and minima, because if you smoothen them, you're just going up, not a critical point. And these are the level curves. These are topologically equivalent deformation retracts of sublevel sets of deformation retract. And here we have some level curves that are disappearing, so probably a critical point. Let me, scroll quickly to show you some steps of application of our simple theorem 1. So we start with this, and we want to analyze doubly degenerate critical points. So critical points that on the rest of the surfaces where eigenvalues are simple, you kind of have to differentiate the eigenvalue with respect to parameter, do the classical thing. And it's actually more difficult in this case than looking at doubly degenerate eigenvalues. Why? Because 2x2 matrix has doubly degenerate eigenvalues only if it is proportional to identity. So we look when this can be proportional to identity, so this has to vanish. So we are on a circle, and these have to vanish, otherwise they're two different numbers and should be the same. So z is equal to 0. So this is a circle in the parameter space on top of which the eigenvalue multiplicity 2 lives. That's what we saw on this circle on the Mexican hand pictures. So this is a submanifold on which eigenvalues have multiplicity, but not all of them are critical points. So we need to find the critical points on this guy. So for this, we just take partial derivatives of the matrix, and the condition for critical point, sufficient condition for critical point, was that the span of these guys has codimension 1. There are 3 2x2, the 2x2 real symmetric matrices have dimension 3. So I have 3 guys here, so I'm looking to drop a dimension. The dimension of the span of these guys, you just look at them and do a bit of linear algebra, is 3 unless this guy vanishes identically. So y needs to be equal to 0 for us to have a candidate for the critical point. So y is equal to 0. There's these 2 points. And then furthermore, we should determine whether it's a critical point or sort of fake critical point, which is too tilted. We look at the orthogonal complement. We compute it to be this. We x here is equal to plus or minus 1, depending on whether we are here or here. And then we'll look at whether it's positive definite or not. So it is positive definite if c in absolute value is smaller than 2. So that's what we saw in the pictures. C smaller than 2 here, yes, they're critical points. C bigger than 2, they're not critical points because they smoothen to just increasing function. But we got it just by doing calculus. So that was the purpose of the theorem, reduce it to calculus. Okay, and the last 9-10 minutes, I quickly present the much more difficult and chunkier result. So I started by explaining what are Morse inequalities. And they allow us to get so if we know what manifold it is, for example, we can estimate the number of critical points. Or if we know how many critical points we're getting, we can estimate the complexity of the manifold. It can go both ways. So this is how to give index to a critical point of an eigenvalue experiencing a point of multiplicity. We use first theorem. We think it's a critical point. What is its index? For this, I need a bit of more terminology. So I remind you that nu is the multiplicity of the eigenvalue, and I will be the relative index of the eigenvalue, counting from above in the following sense. So here, I'm looking at this black curve, lambda k. This is my eigenvalue of interest. And at this point, it experiences point of double multiplicity. So nu is equal to 2. And the black curve is the first curve from above. So I is equal to 1. Its relative index is 1. Here it is experiencing multiplicity 3. And there is top one, its middle, and then there is a bottom one. So its relative index is second from the top. And here multiplicity is 3, and black curve is third from the top. So this is the definition of I in pictures. And I have this formula. The meaning of this formula is the dimension of all self-adjoint matrices of size I by I minus 1. And it's actually a dimension of matrices with ith degenerate eigenvalue in the higher dimensional space. There is also a q factorial, which is given by this formula. It's actually a polynomial in q, despite having a denominator. It all cancels, kind of like binomial coefficients. They're integers despite being represented by a fraction. So it's a polynomial in q that will be necessary in the next slide. So this is the second derivative test. The upshot of this theorem, it looks complicated. I'm not showing it to you to scare you. I'm showing it to you to prove, to kind of convince you that I have all formulas. We have all formulas worked out. So what's interesting is that really there is not so much variation. You cannot. It's not like for smooth functions where the point can have any multiplicity, any index whatsoever. Here, the point will have certain index which only depends on the multiplicity of the point and which curve we're looking at. So the middle curve will have a certain index always. If it's a critical point, then it's always the same index. The top curve, if it's a critical point, then it's always a minimum. There is no variability. There is universality that in terms of multiplicity and this relative index. However, the index itself is not so simple. So index itself is some sort of polynomial in t to the power 4. So, but there is a formula. There is a formula. It depends on a few things, whether we are doing over reals or over complex numbers. Over complex numbers, as usual, answers are a lot simpler. Over reals, there are some 3 cases that we have to struggle with. This 0 is interesting because like if the contribution is non-zero, then it means there is a critical point because the topology experiences a non-trivial change. 0 suggests that maybe nothing is happening there. But this 0 is misleading. It's not actually 0. It's just because we're doing homology over integers. There is some universal contribution SI. This is the formula I showed before. And there is this T mu contribution that comes from smooth directions. As in the example that I described, like when we had a whole curve of critical points, a whole curve of points of multiplicity. If you look at, I don't know, first there are 2 eigenvalues, and they coincide on this curve in parameter space. So if you look at this eigenvalue along the curve, the eigenvalue is smooth. It experiences non-smoothness only if we move away from this stratum of the same multiplicity. these answers are only for these non-smooth directions. Along the smooth part, it can be like, really, it's a smooth function on one-dimensional manifold. It can be a minimum or it can be a maximum. And this mu is from contribution of the smooth directions. Of course, smooth directions are non-universal, non-smooth directions are universal. That's the upshot of this theorem. And to just show you some examples of computed values from here for the real case. It's this table in multiplicity 2, the upper surface always has a minimum. It's not actually trivial to prove. This does not say it's a minimum, but it suggests it's a minimum. And the lower surface always has a maximum, and 2 is the dimension of the non-smooth directions. If we have a triple intersection, then the upper one has a minimum, the lower one has a maximum. It's in 5. There are 5 non-smooth directions, and the middle one is indeterminate. It's a critical point, but it doesn't contribute anything to this Morse counting in Morse inequalities business. And so it goes, and then later you encounter a case where a critical point contributes 2 indices at the same time, which is natural. We have some really complicated topologies here, and we're just describing it in terms of indices. So it's like a 5 index 5 point and an index 9 point in the same point. It's like a merger of the 2 points. Actually, this 0 can be interpreted as a merger of 2 points as well, but this merger just annihilates them. Kind of, they disappear, leaving some crazy remnants. And this 5th and 9th index are too far away, so they cannot disappear. They stick around. All right, some last-minute disclaimers for our results. I skipped a lot of terms and conditions. All the above is for generic families only. So we have some conditions on what is generic, and the further questions, of course, involve include the questions of what happens in the non-generic case. What if there is some generic eigenvalue multiplicity, but then there is symmetry forcing us to be non-generic? Maybe if we understand the symmetry that is forcing non-genericity, we can understand more. And something I described already, the zeros here are not completely zero. It doesn't mean it's not a critical point. It is a critical point. It's just the integer homology does not capture what is happening there. You need to look at Z2 homology. That is all I wanted to say. So thank you for your attention, and thank you to the organizers.
Thank you very much, Grisha, for nice talk. Questions, please.
May I? Grisha, where is the difference between odd and even mu come from? Because some have zeros, some do not have, well, zeros, quotation marks.
Yes. I can explain where it comes from in the proof, but kind of intuitive explanation I do not have yet. There is some in the proof we do some retractions, and then we get down to some manifolds, that the manifolds of matrices with in the sublevel set, and then the manifold can either be orientable or non-orientable, and this creates a difference. But a nice humanly understandable explanation I do not have, but it's not untypical that in the real case there are the two or more cases in homology calculations compared to the complex case.
Okay, thank you.
More questions, please.
But really, I think more can be understood. And I had some pictures, but they got mangled up in preparation. More can be understood in terms of like the zeros could be understood by perturbation. So this is some sort of picture of the middle sheet, and it looks like it has doesn't have a critical point, but I'm plotting 2 dimensions out of 5, so there's more stuff going on. But if we perturb the matrix a little bit, you resolve this triple degeneracy into 3 double degeneracies, and then combining this indices, some magic happens on 0. They cancel. But we have not worked out the complete picture.
Okay, thanks.
Thank you. Other question, please?
I'm sorry, can I ask one question?
As many as you like, Pavel. We don't hear you. Yeah, I think we lost
some connection problems. Yes. Okay, so if we do not have other questions, so thank you very much again, Grisha, for a nice talk. It is so today's session is over. Thank you to everybody and see you tomorrow.
Okay. Let me just remind you that the lectures are in the YouTube and Facebook channels of EMAS if you would like to listen to them, right? So we meet at 9, as always, Mexican time.
Okay,
Uh,
bye-bye.
So bye-bye. If there's no more comments, then I will close the session. Okay, so see you tomorrow. Bye-bye.
See you tomorrow.
Bye.